Hello, and welcome back to another episode of the natural number game in Lean 4. Today we'll be starting the inequality world. Well, to start the inequality, we need to have a notion of inequality. And we're going to have a new definition where if a and b are natural numbers, we're going to define a less than or equal to b. So let's do just that. Let's get our natural numbers. And we're going to define less than or equal between a and b being natural numbers. Say if there exists a c belonging to our natural numbers, b is defined to be a plus c. So what is this saying? This is saying that, well, if a is less than b, less than or equal to b, there exists a natural number c such that b can be written as a plus c. So if a is 1, b is 2, then c is 1. If a is 2, b is 2, then c is 0. Notice that for natural numbers we don't have negative numbers, so we can't have a be bigger than b. And now we're going to have our instance less than or equal to for our natural numbers, where less than or equal to is defined to be or less than or equal to. And that lets us have a new theorem. Less than if and only if exists add a, b natural numbers. That says a less than or equal to b if and only if, with this line, there exists c in n such that b equals a plus c. So this is saying that, okay, what is this if and only if or equal to? Well, we have our definition of less than up here, and this is just saying that, okay, a less than or equal to b is the same as that. And then if you notice, what is this less than or equal to? Well, this, by this macro expansion, is just the binary relation on capital LE dot LE. So we know that this and this are the same thing, because we defined that this LE here is capital LE dot LE. So we can just use if and only if dot REFL. And that's our proof of a very useful theorem that we'll use for the inequality world. Okay, now we have our LE.lean, and then we can go to close this. And then, yeah, because we have this instance, we can use this less than or equal to, because if we don't have it, it's a failed synthesized instance. LE is like capital N in Gothic font, which is our natural numbers. Nice. And now let's open up inequality world. So we'll start with level 1 of the inequality world, and then we're gonna open mynat.le, or import open mynat. Nice. So we saw that there exists, and we're gonna learn about tactic with it. So let's see. We're gonna have a lemma 1 add less than self x. Defined as a natural number that x is less than or equal to 1 plus x. Sorry. So how do we do this? Okay. First, we can turn the goal explicitly into an existence problem with rewrite or RW. What is it? Is it rewrite? Yeah, rewrite. And we need a list. Rewrite which lemma. Well, we have our LE if exists add. So we be in tactic mode. Okay, so before we had this as our goal, and now with rewriting we just directly turn it into there exists a C such that 1 plus x equals x plus c. Okay. Clearly the statement is true. Yep, there does exist a C such that 1 plus x equals x plus c with c equals 1. So the use tactic can be used on goals of the form there exists C ... The idea is we choose which natural number we want to use and then we use it. So if we do use 1, that would be how it would be for lean let C equals 1. Does that work? Okay, let me figure out what the lean 3 would be just used, but let's figure out what the corresponding tactic is for lean 4. Okay, so the tactic we can use is exists. So we can do exists 1 to change it from C to 1. And oops, no comma. And then now we have x plus 1 equals 1 plus x. So we can rewrite with add commutative. Import mynet, import mynet dot addition world, and then reflexive. And there's our proof for our first lemma, 1 add less than self 1f. And then we learned about the exists. And then an important time saver here. Let's see if we can do this. Can we comment this line out? We can. So we can go from here to here because it's just defined there. If and only if reflexively, it's just defined to be the same thing. So we actually don't even need to use this less than if and only if exists addition. Cool. Let's delete this line. Let's move on to the next level. Less than or equal to reflexive. Okay. Okay, I have an idea how to solve this. Less than reflexive x belongs to n. Oops. N x is less than or equal to x by exists 0. Cool. I think exists tries trivial at the end, which like kind of similar to reflexive. And there's this refined thing, which is a bit more involved, which I'm not too sure how it works, but not important for this. Cool, that was easy and fast. Less than, successor of less than. Interesting. So let's try this one. Theorem, less than successor, a, b, both natural numbers, and we'll define a less than b implies a less than or equal to successor of b. Okay, that makes sense. But because if it's less than b or less than b plus 1, I don't think I need these parentheses, so I'm going to delete them. Okay. Sorry. Cool. Let's see what we can do here, well, if we intro H, our hypothesis, we have our hypothesis contain this A less than or equal to B. Okay. So one thing that we can do to make this a little bit easier is you do, let's see, rewrite less than if and only if exists at H at H. Can we do this? Vertical bar, horizontal bar. Before is this, after is this, and if I don't have this at H, what happens? Okay, so it doesn't do it at H. And then what if I don't have this? Doesn't do there too. Cool, cool. So does it at both the hypothesis and at the goal, oops, and at the goal itself. Oh, backslash goal could work. Cool. So you can have this. There exists a C, where B equals A plus C, and then that's our hypothesis, and then our goal is there exists a C such a successor of B equals A plus C. Well, if we get the C, then successor of C should be the second C. There's like C plus 1. Can we get this C from H somehow? Can we like, yeah, let's see what we can do. Because we can do some cases. Cases H, C, cases H, and then with sorry, what should the first thing be? A? Okay, so this has, let's see, intro. Okay, so let's see, this is C is a number, and then hypothesis prime. Okay. Cool. So now we have A, B, C natural numbers, and then we have our hypothesis prime that B equals A plus C. And now we need to show that there exists a C such a successor of B equals A plus C. I think here we can do something like exists successor of C. Okay, that gets somewhere. So now we have successor of B equals A plus successor of C, and our H prime is B equals A plus C. Now we can just rewrite H at B. So rewrite H prime. And then we can also use like add successor. Cool, and then ruffle. And that's our proof. And then I'm guessing we actually don't even need this rewrite. Nice. So here's our nice little proof. Okay, so we intro H. We do cases on H with. So on there exists we can do cases, and that's with our we get our existential qualifier that we pin that C, and then we have our H prime. And now with that we can just say that okay, we'll use successor of C because that's from C to successor of C to get A is less than successor of B is what we want. And then we can just use our regular proofs and lemmas and stuff to finish our proof. Nice, that's less than successor. A nice little theorem. Okay, 0 less than, okay. Lemma 0 less than A is a natural number. Oops, don't want that. A is defined to be a natural. We want 0 to be less than or equal to A by like we kind of want to split A into cases where it's 0 or and then it's equal or it's successor of something, and then like prove that by contradiction or something. So cases A with 0 successor A prime. Okay. 0 less than or equal to 0. Let's just do maybe 0 here. Can I do ruffle? Oh, I can do LE ruffle. Okay, let me try to. Let's see. Exact or rewrite LE ruffle. Let me just do 0 then. Oh, why did that not work? Exact. Okay. And what if this is 0? Nice, okay, that works too. Exact LE ruffle 0. Forgot how to use that exact tactic again. Then what about this case? Successor A prime. Lemma 1 had 1 add less than or equal to successor. I guess we continuously use this. We can say like this is 0 plus something, and that's less than that by this, but that seems kind of hard. Less than or equal to reflexive doesn't make sense in this situation. So probably want to use less than successor here. A less than B implies that A is less than or equal to successor of B. Not A is less than successor of B implies. So we know 0 is less than 0, less than or equal to 0, implies that 0 is less than or equal to successor of B. Maybe we could use induction actually. Instead of cases, induction A 0H. Okay, here we go. We want to do induction instead of just cases. Now we have our inductive hypothesis, and then now we can use less than or equal to successor. Exact less than or equal to successor A prime. Less than or equal to successor takes two things. We want 0 and A prime. 0 A prime. No parentheses maybe. What's wrong here? Oh, okay, let's try to do 0. No. 0 0. Let's see. Oh, we need h. Okay, I forgot to pass in h as well. Okay, that's actually really nifty. We just use less than reflexive here, and we use less than successor here with our inductive hypothesis on A. Great. That wasn't too bad. Less than or equal to transitive theorem, less than or equal to transitive A, B, C, all natural numbers. HAB is defined to be A is less than or equal to B. HBC is defined to be B less than or equal to C. More show that A less than or equal to C. Okay, let's sorry. Why did I spell theorem wrong? Yes, I did. Theorem. Let's move this down here. By. Okay, so we have A less than or equal to B, B less than or equal to C. Okay, let's think. Okay, so we want to cases HAB with intro, I don't know, D HAB prime. What does that give access to? 2. Okay. So B equals A plus D. Now let's also do another cases HBC with intro ABCDE HBD prime into, okay. I need to indent you. No. Why did this not work? Oh, no, HBC. HBC. Okay. Now we have B equals A plus D and C equals B plus E. So now we want to do A is less than or equal to C. We want to use so if A is less than or equal to C, then C equals A plus something. C equals A plus D plus E. So we want to do exists D plus E. Okay, C equals A plus D plus E. Okay, and then we could do rewrite HAB prime backwards. HAB prime. Or okay, this equals that. Oh, okay, so we want to add com. No, add, what would this be? Add associative, but like in reverse. Okay. HAB in reverse. Okay. And then exact HBC prime. Cool. And that's our proof, less than or equal to transitive. So stepping through it, we have our named hypotheses. We do cases on the first one. They get D and HAB prime. We do cases on the second one. They get E and HBC prime. We say, okay, what is C? C equals A plus what? We say C equals A plus D plus E. And then we do some reordering, and then we're done. Cool, and let's see what the next level is. Nice. Okay, so I think this is a pretty good stopping point for this episode. We'll be proving less than or equal to antisymmetric next, such that if A is less than or equal to B and B is less than or equal to A equals B. So stick around for that next time, but today we'll do a quick recap of what we did today. So first off, we defined less than or equal to and said that, okay, it's an instance of this less than or equal to, and we had a theorem for what it means to be less than or equal to and how it relates to this symbol. And what less than or equal to just precisely means that B equals A plus C with a C that exists, and this lets us use our symbol here, and this shows the equivalence between the symbol here and this statement. And then this could have been just as easily LEAB, but we can just use our symbol instead. That's a little nicer for mathematicians to use that notation. And then we proved a bunch of lemmas and theorems related to less than or equal to. Nice. Thanks so much for watching, and join us next time. Join me and you next time to prove some more theorems about inequalities.